Hey folks, welcome to our unit on momentum. This unit and the energy unit represent applications of Newton's second law, and each unit has a conservation law at its center. Each unit also has a concept that involves a change in the quantity we're studying. So as we go through the momentum unit, I want you to remember the words that we use in the energy unit. We said that work results in a change in mechanical energy. In the absence of work done by non-conservative forces, the mechanical energy is constant. We will say very similar things in this unit, and so kind of be on the lookout for that sort of thing in this unit. So this unit is about momentum, and so we're going to start by talking about the two main vocab words in this unit, impulse and momentum. Because Newton's second law kind of informs more or less everything that we do in this course, we're going to start with Newton's second law. And so the first thing we're going to do is derive expressions for impulse and momentum. They're kind of baked into Newton's second law already, so it's a pretty simple derivation. So we have net force equals mass times acceleration, so a net force causes acceleration. Um, in this unit especially, the forces that are exerted are not constant, but every force, no matter if it's constant or changing, has an average. And so if I put this little hat on the letter F, this hat means average force. Then I have this idea that even if I just consider the average force, it's the same basic idea that now if we deal with a variable force, the average is still a value that is a placeholder for the overall force. The other concept that I wanted to remind you of is acceleration. Acceleration is the rate at which velocity changes, and so delta v over delta t. So the change in velocity divided by the amount of time that it takes the velocity to make that change. And all I'm going to do is one little substitution. Because of the definition of acceleration, I can rewrite Newton's second law as this. The average net force equals the mass times the change in velocity divided by the amount of time that passes when this is happening. And if I multiply both sides by time, I get the net average force times time equals the mass times the change in velocity. And so this is one of the biggest ideas in this unit, is that an average net force over some amount of time causes the mass to change its velocity. And within this equation, we have two vocab words and basically two big ideas. So if we take the force times time part of that equation, that multiplication of force and time is given the name impulse. So, a force is just a force. A force exerted over some distance we call work. A force exerted over some amount of time is called impulse. The variable for impulse changes depending on what textbook you are using. I don't actually know that it's declared in ours. I think it's probably J if it is. But J for impulse doesn't make a lot of sense, but whatever. And that's equal to the average, and I'll rewrite it this way, the average force exerted times the time. And so that's our first vocab word of the unit is impulse. So a force exerted over a certain amount of time is an impulse. You can have an impulse by an individual force or a net force. In AP Physics 1, they're pretty much the same, that if there's an impulse, it is due to the net force. Okay, impulse is a vector. Because force is a vector, even if you multiply it by time, it's still a vector. So because a force has to point in a specific direction, an impulse also has to be exerted in a specific direction. As far as the units of impulse, force times time, that would be Newton seconds. So newtons times seconds is the unit. That does not have a fancy name. So Newton seconds, that's it. Okay, so that's impulse. The second one, if I take the m times delta v, the idea in here is called momentum. Momentum gets the lowercase letter p, and it's equal to mass times velocity. So just a quick clarification that we will look at in a minute. This is delta v. So technically this would represent the change in momentum because velocity is changing. But if we take out the context and just say this m times v quantity, that is what is called momentum. So an object can have momentum as long as it has a mass and a velocity. When you get into quantum mechanics, it doesn't even need to have a mass to have a momentum, just has to be moving. So every object that is moving has momentum. The larger the mass or the larger the velocity, the larger the momentum could be. So, like a dart being thrown, if it's thrown really fast, even if it has a small momentum, it can a dart, even though it has a small mass, if it's thrown with a large velocity, it can have a lot of momentum. Conversely, if you have like an ocean liner, like the Titanic, let's say, just sitting there, it has a lot of mass but no velocity, so it has no momentum. A little bit more about momentum in a minute, but momentum is also a vector. So in the energy unit, we were dealing with scalar quantities. We were just keeping track of a number from time to time and seeing how it changed or didn't change. With momentum, the thing that makes this unit tricky is that it is a vector, so the direction of everything matters. The unit for momentum, mass times velocity, so that's kilograms times meters per second. So we get kilogram meters per second. Now, one of the things about physics equations is that they have to be dimensionally consistent. So let me show you that the left side and the right side of this equation are in fact dimensionally consistent. A Newton is equal to a kilogram meter per second squared. Remember that net force equals mass times acceleration. So a Newton second is going to equal a kilogram times meters times seconds divided by seconds squared, right? So newtons times seconds, one of those seconds cancels, and so a Newton second is equal to a kilogram meter per second. What does that mean for you? That means it doesn't matter what units you use for impulse, and it also doesn't matter what units you use for momentum. Newton seconds or kilogram meters per second are both valid, so you need to be on the lookout for both of them. Kilogram meters per second is more common, but what you will see is that I will tend to use Newton seconds for impulse, and I will tend to use kilogram meters per second for momentum, and you just need to know the same thing, that they are dimensionally equivalent. Okay, great. The last thing for this video is this idea of momentum. Momentum is, it's actually was part of Newton's second law originally. And so, velocity is how fast something's moving and in what direction. If you add mass to it, it gets a little bit harder to define. It's often referred to as the quantity of motion. But the way that I like to think of it is the way that I was taught to think of it is like the more momentum something has, the harder it's going to hit you, or the more hurt it's going to cause in a collision. And so, it can be like a baseball thrown at 90 miles an hour really hurts when it hits you. And so, something that has not a lot of mass, but a lot of velocity is going to hit pretty hard. Same thing with a car going like 2 miles an hour. It's not going very fast, but it has a huge amount of mass, and so it has a lot of momentum, and so if it hits you, you're going to feel it. You will feel those two things in different ways, but that's other physics concepts entering into it. So momentum is like how hard something hits if it hits. And so that's the end of our first video. Next video up is on the relationship between impulse and momentum.